Mr. Schultz here. Chatelier's principle is what we're going to talk about. We know that an equilibrium is an equation where the rate of the forward reaction is equal to the rate of the reverse reaction. Chatelier said that if we added concentrations or changed the concentrations, we changed the temperature, or we changed the volume, or we changed the pressure, that there would be a shift in the direction that relieves that stress. The shift would either be in the forward or reverse direction. I'm going to just show you what Le Chatelier came up with. There's a little video on the next slide here about dynamic equilibrium. If you want to know a little bit more about dynamic equilibrium, you can look at it on the PowerPoint that I have sent to you in Google Docs. Well, the first thing that Le Chatelier said was that if we added or removed a reactant, there would be a shift. If we add a reactant, the first thing that happens is we have extra reactant, we have extra A or B or both. And it will cause the teeter-totter or cause the reaction to be heavy on the left side. Therefore, to equal it out, it'll shift to the right side to make more product. Same thing happens if we remove reactant, or the opposite happens. If we remove A or B or both, then the teeter-totter shifts towards the C and D section, and the equilibrium shifts to the left to make more reactant. With the product, if we add product, we add more C or D or both, then the equilibrium shifts towards the product, or sorry, the reaction shifts towards the product, and the equilibrium will shift to the left to make more reactant to equal it out. If we remove product, if we remove C or D, the teeter-totter will be heavier on the A and B section, and the equilibrium will shift to the right to make more product. So a little video that shows this demonstration. I'll quickly show it to you and stop it when I need to. It's by NCSSM. This is a gentleman introducing the concept. In this reaction we have iron and sulfur cyanide, and when we react those two things together, we have a reddish orange at equilibrium. So we have a control on the left here, and we're going to add iron to the second test tube, and we can see a shift in the equilibrium towards iron sulfur cyanide. So what happens if we do this again and we still have that control, but this time let's say we added SCN. Again, we're going to shift towards the product side to get rid of the SCN. Finally, we're going to add some OH. You can see it turning pale yellow, which is the color of the iron. It's obviously shifting towards the reactant side. Let's see the actual equation to show you what's going to happen, and we'll stir it up. So the OH actually reacts with the iron and removes iron, so therefore it because we're removing reactant. Here we're adding KCl. Let's see what happens with KCl. KCl reacts with iron again to the iron and the K do a double replacement reaction. And again, we're removing iron. Finally, we're adding some silver, and we see a white precipitate form. And again, this white precipitate is reacting with the SCN negative, forming a solid, removing SCN negative. So again, we're going to be shifting towards the reactant side. Mercury again, removing SCN negative. So I've just shown you either adding reactants or taking reactants away and the effect that they have. What about change in temperature? It depends if we have an exothermic or endothermic reaction. Exothermic reactions, if you remember, is energy is written on the right-hand side. Therefore, it's a product. If we increase the temperature, we are increasing the product and making the product heavier. Therefore, it's going to shift to the left to make more reactant. If we remove temperature, we are removing some of the energy, and A and B is getting heavier, and so we're going to shift to the right to make more product. So just treat temperature like it was a reactant. In endothermic reactions, the opposite happens. If energy is on the left-hand side now, so if we remove energy, in other words, it gets colder, then we are actually removing energy from the, if the energy goes down or the temperature goes down, we're removing energy from the left-hand side. The right-hand side gets heavier, and we have to shift to make more reactant. If we increase the temperature on the left-hand side, then that means the left-hand side becomes heavier, and we shift to the right to make more product. Here's an example of a demo showing you temperature change.
We start this experiment with 3 tubes containing red-brown NO2 and colorless N2O4 in equilibrium. First, one tube is placed in hot water. A second tube is placed in cold ice water. After a few moments, we note that the tube in hot water has darkened in color. It now contains more brown NO2 than the tube which we kept at room temperature. The tube in ice water has less brown NO2 in it. It is much paler because the equilibrium has shifted to favor the formation of colorless N2O4.
So we're adding energy on the left-hand side, and we're taking energy away on the right-hand side. We're adding energy on the right-hand side, or on the left-hand side of the picture here, and it's shifting towards the NO2. Last thing we're going to look at is what happens if we have a change in volume and pressure. This happens only with gases, and it happens when there's unequal amounts of moles. If we have more moles on the left-hand side and we increase the volume, that is like we're giving it more space, and therefore we're giving it the one with the side with more volumes is actually becoming lighter, and therefore it rises. And it will shift and make more reactant. If we decrease the volume or increase the pressure, make it into a smaller and tighter space, then we shift, the left side becomes heavier because the, remember, concentration is moles per liter, and the liter is getting smaller, so therefore the concentration is getting larger. So because the concentration is getting larger on the left, because there's more moles on the left, it will be heavier and it will shift to the right to make more product. The only exception to this is when you add an inert gas that increases the pressure but does not change the volume, and therefore does not change the concentration. There has to be a change in concentration for this Le Chatelier's principle to work. And the opposite, if there's more moles on the right-hand side and we increase the volume, that means that we're making the right-hand side lighter, and it goes up, and it will shift to the right to make more product. If we decrease the volume or increase the pressure, they're related, by the way, then the right-hand side becomes heavier and sinks to the ground, and we shift to the left to make more reactant. Hopefully this has helped you understand Le Chatelier's principle. I'm going to end off with another little video, Le Chatelier's principle animation, which will kind of summarize everything we've talked about.
Systems in dynamic equilibrium are very sensitive to changes in concentration, pressure, and temperature. Le Chatelier's principle enables us to predict the effect of these changes. It states that if a system in dynamic equilibrium is disturbed, the equilibrium position shifts to counteract the disturbance. For example, if more reactants are added, the system removes them by creating more products. If products are removed, the system replaces them by converting reactants. Consider the Haber process, in which nitrogen and hydrogen react to form ammonia. The Chatelier's principle tells us that if the pressure on the system increases, the equilibrium position shifts to the side where there are fewer moles of gas, and hence a lower pressure. The forward reaction is exothermic. Energy is released when ammonia is formed. Increasing the temperature drives the equilibrium position to the endothermic left-hand side, as the system absorbs additional heat energy from the surroundings. Decreasing the temperature drives the equilibrium position towards the exothermic right-hand side. The system gives heat energy back to the surroundings. A better yield is obtained at lower temperatures, but this benefit is offset by a slower reaction. Industrially, a temperature of 450 degrees Celsius, a pressure of 200 atmospheres, and an iron catalyst is used.
All right, that's it.